In today's video, we'll be comparing simple harmonic motion with uniform circular motion. So how is simple harmonic motion related to uniform circular motion? So if you did a quick experiment, and if you had a ball attached to the rim of a turntable, which we have illustrated in our figure to the right, and it is illuminated from the side, we see that as the turntable rotates at a constant angular speed, the shadow of the ball moves back and forth, creating a simple harmonic motion. So with this relation, we can find the position as a function of time. So we see that our displacement will equal our amplitude multiplied by cosine of theta. And since theta is equal to our angular speed multiplied by time, and our angular speed is the same as 2 pi over t, and the inverse of t is frequency, we see we can substitute 2 pi multiplied by a frequency times time and for theta to get an equation to calculate our position as a function of time. We then see we can find velocity as a function of time as well as acceleration as a function of time. We're also able to calculate the period of oscillation, the frequency, and angular frequency. So our period of oscillation is the time required for an object of mass attached to a spring with a constant spring constant to complete one full circle. And this can be described with the equation that our period is equal to 2 pi multiplied by the square root of our mass divided by our spring constant. Now, if we look at frequency, the frequency gives the number of cycles per second. And since we know frequency is just the inverse of our period, we can take our equation for the period of oscillation and take the inverse of it, which will give us the equation that 1 over 2 pi is equal to the square root of our spring constant divided by our mass. And then finally, we see that angular frequency gives the number of radians per second. So we see that our angular speed is equal to 2 pi multiplied by our frequency, which is the same as taking the square root of our spring constant, dividing it by our mass. And when we make these calculations, it's important to remember that our calculators must be in our radian mode and not our degree mode. So knowing this, let's look at our first example. It states that the period of motion of an object spring system is 0.223 seconds when a 35.4 gram object is attached to the spring. What is the force constant of the spring? So we're given that our period for our spring system is equal to 0.223 seconds and that the mass of our object is equal to 35.4 grams. And we're asked to solve for the force constant. So we're trying to solve for Rk. So out of the equations we know, there's one equation that has all three of our variables of interest. And this equation is that our period is equal to 2 pi multiplied by the square root of our mass divided by our force constant. And so we can divide 2 pi by both sides, which will give us our period divided by 2 pi equal to the square root of m divided by k. And if we square both sides, we'll get the equation that our period squared divided by 2 pi squared is equal to m over k. And then if we multiply both sides by their inverse, we'll get a new equation that states that K divided by M is equal to 2 pi squared over our period squared. And if we multiply each side by M, we would get our final equation that states that our K is equal to 4 pi squared divided by our period squared multiplied by our mass. So now we can plug in our values given. So we have 4 pi squared divided by our period squared of 0.223 seconds squared times our mass once converted to kilograms of 0.0354 kilograms. So if we multiply this out, we see that our force constant will be equal to 28.1 newtons per meter. In our second example, it states that a 2 kilogram object on a frictionless horizontal track is attached to the end of a horizontal spring whose force constant is 5 newtons per meter. The object is displaced 3 meters to the right from its equilibrium position and then released, initiating a simple harmonic motion. What is the force, magnitude, and direction acting on the object after 3.5 seconds after it is released? So in part A, we can start by summarizing our information, given that the mass of our object is 2 kilograms and that our spring constant is equal to 5 newtons per meter with a displacement of 3 meters over a period of 3.5 seconds. And we're asked to find the force. So since we're dealing with a spring, we can use Hooke's law, which states that our force is equal to our negative spring constant multiplied by our displacement. So we know our spring constant, which is K, and we're given X, but we can't use our change in our displacement since it's in a simple harmonic motion. So when we're trying to find the position in a simple harmonic motion, we know that X is equal to our amplitude multiplied by our cosine times our angular speed multiplied by time. So we have our time, and our amplitude is our actual displacement of the spring, but we don't have our angular speed. But we know that angular speed is also equal to the square root of K divided by M. So which we can plug in our angular speed. So we can plug this part of our equation for W and this X into our Hooke's law. So we'd get an equation that our force is actually equal to our negative spring constant times our amplitude multiplied by cosine of the square root of K divided by M multiplied by our time. All our values are known besides force. We can solve for our force. So our spring constant was 5 newtons per meter with an amplitude of 3 meters times the cosine of the square root of our spring constant of 5 divided by our mass of 2 kilograms multiplied by our period of time, which was 3.5 seconds. And now if we calculate this through, we see that our force will be equal to negative 11 newtons. Or we can say the force is 11 newtons acting in the left direction. In part B, we're asked how many times does the object oscillate in 3.5 seconds. So we know that frequency is the number of cycles per second times our change in time will equal our number of oscillations in our time period, which we know that frequency is just the inverse of our period times our time will give us our number of cycles. So we know our time, we don't know our period, however, so we can use the equation that our period is equal to 2 pi times the square root of our mass divided by our spring constant. Our two variables are known, so we can solve for our period. So when we plug in the information we're given that the mass is 2 kilograms divided by our spring constant of 5 newtons per meter will give us a period of 3.9738. Now that we know our period, we can plug it into this following equation that states that our change in time divided by our period is equal to the number of times the object oscillates. So if we plug in our time of 3.5 seconds divided by our period of 3.9738, we'll get that our number times oscillations is equal to 0.881 oscillations.